magnetic induction and EMI and शॉर्ट में उसको बोलते हैं EMI and then AC alternating current popularly known as EMI and AC. Okay, so before we start EMI, electromagnetic induction, I would like to give you the concept of magnetic flux. What is magnetic flux? Magnetic flux. Now you know electric flux. What was that? Electric flux. It is a dot product of electric field and area vector. Similarly, magnetic flux is nothing but dot product of magnetic field and area vector. In other words, you can define total number of magnetic lines of force passing perpendicularly through a given area, given surface. That is called magnetic flux, denoted by a symbol phi. So it is the total number, total number of magnetic field lines crossing normally means perpendicularly through a given surface. So what I mean to say, or you can define it, flux phi is equal to magnetic flux can also be defined as dot product, dot and cross product, you know it very well, dot product of magnetic field and area vector. Now if in a uniform magnetic field, so suppose you have a uniform magnetic field, okay, and some area is placed like this, some surface is placed like this, then magnetic field and area vector, you know, area vector is always perpendicular to the surface pointing outward. This is area vector and this is the direction of magnetic field. Now there is some angle between magnetic field and area vector. That angle is theta. Then flux is defined as, that is the component of magnetic field passing perpendicularly through this surface. So if you resolve vector B in the direction of vector A, the component will be B cos theta. And that component will passing through this given surface normally, means perpendicularly. So B cos theta, you have to take the normal component of magnetic field multiplied by area. So this is BA cos theta, also known as B dot A, dot product of magnetic field intensity and area vector. Magnetic field phi is a scalar quantity, and before we start writing its unit, let us know if theta is 0 degree. If theta is 0 degree, you know, flux is simply B into A. And if theta is 180 degree, then flux is minus BA. And if theta is 90 degree, then flux is 0. No flux is there. Okay. So if the magnetic field is 0 degree, what does it mean? Magnetic field 0 degree means, theta is 0 degree means, this is the magnetic field and here is your surface. Now magnetic field and area vector are along same direction. Here theta is 0. This is the case. Okay. If the area vector and magnetic field are opposite to each other, so in that case, if area vector is along this direction, magnetic field is along this direction, then phi will be minus b into a. And if theta is 90 degree, so 90 degree means surface is placed like this. And then magnetic field vector is along this direction, area vector is along this direction, this angle is 90 degree. So this is the case when flux becomes 0. Now what is the unit of magnetic flux? Unit of magnetic flux. Unit of magnetic flux. So how can you write the unit? Phi is equal to b into a. So unit of b is Tesla and for area it is meter square. So SI unit is Tesla meter square. Tesla meter square. And it is a scalar quantity. It is a scalar quantity. Remember electric flux, that was also scalar quantity. So it is a scalar quantity. Their addition follows algebraic addition, scalar quantity. So you need not to worry about the vector addition, no direction, scalar. So when magnetic flux, now this chapter has a deep concept of magnetic flux, as well as whenever magnetic flux linked with the surface loop circuit changes, then some electric current, electric EMF you can say, electromagnetic force, EMF, electric current also is generated in the circuit. This was first observed by Faraday, known as Faraday's observation. So take the snapshot, I will rub it. Faraday's observation. Now we are talking about the Faraday's observation. So Michael Faraday, Newton, Einstein, Faraday, father of physics, great scientist, large contribution in the field of physics. Now I am talking about Faraday's observation. So what the Faraday did, he just took a coil, okay, and a galvanometer is connected across two terminals of the coil, like this. This is a galvanometer, okay, and a magnet, bar magnet, north-south. So if the bar magnet is brought towards the coil, the scenario is very simple to understand. If you have a coil like this, and these two ends are connected with the ends of galvanometer, okay, and this is the bar magnet, and if you bring the bar magnet towards the coil, then galvanometer shows deflection, and you know galvanometer shows deflection only when some current flows through it. Though galvanometer is a very sensitive device, even a small current shows large deflection. So when north pole or this bar magnet is brought towards the coil, in galvanometer you will observe some deflection. On the other hand, when the magnet is brought away from the coil, now you were bringing the magnet towards the coil, now you are bringing the magnet away from the coil. Separation between the magnet and the coil is going to be increased. Then also the galvanometer is showing deflection. But the only thing is, direction of this deflection is just reversed of the earlier deflection. So this phenomena was first observed by Faraday And suppose if you are bringing north pole this side, then deflection is along this direction. If you're bringing north pole away from the magnet, then the deflection will be opposite to this direction. I'm making the another figure also. Okay. So here is your coil. Now galvanometer, and now the deflection is along this direction. If you bring the magnet away, this is north, this is south. Not only this, you can fix the magnet. Don't change the position of magnet, but bring the coil towards the magnet. So if you bring the coil towards the magnet, the separation between magnet and coil is going to be decreased. So in that case also you will have some deflection in the galvanometer. And this is equivalent to the case if you bring the magnet towards the coil, because then also the separation between the coil and the magnet is going to be decreased. So whether you are bringing the magnet towards the coil or you are bringing the coil towards the magnet, keeping the magnet fixed, in both the scenario, one observed the deflection in the galvanometer. The deflection in the galvanometer shows that some electric current is generated. On the other hand, if you bring the magnet away, we are moving it this side. So if you are bringing it away from the coil, what is happening? The separation between the coil and the magnet is going to be increased. So on the other hand, you will find some deflection. But if you fix the magnet and bring the coil away like this, now we are fixing the magnet. Now we are not going to move the magnet, and this is the coil. Now we are changing the position of the coil. So the same thing happens here. Deflection in the galvanometer is along the same direction. Means the separation is increasing. The separation between the coil and the magnet is decreasing. The two conditions are there. But if the separation between the coil and magnet remains fixed, it means there is no relative motion between the coil and the magnet. Then you won't find any deflection in the galvanometer. No matter how many number of turns are there in the coil and how powerful is your magnet. Doesn't matter. Unless and until there is a relative motion between the coil and magnet, one won't find any current in the galvanometer, won't find any current in the coil. This was first observed by Faraday, and it was a great discovery. After that, that AC generator, something like these things are discovered. So, very interesting phenomena, very interesting invention, you can say. So, north and magnet, if you bring the magnet towards the coil, you will find some deflection is there in galvanometer in a particular direction. On the other hand, if the magnet is brought away, then deflection gets reversed. Now see, if north pole is brought towards the magnet, whatever is the direction of deflection, if you bring a south pole of the magnet, say south is this side, north is this side, then deflection gets reversed. Deflection gets reversed. So I am making that figure also. So this is the scenario. Here is galvanometer. Now this time I am bringing south pole of the magnet towards the coil. Then say if north pole is bringing towards the coil, then deflection is towards right. Then if south pole is bringing, then deflection will be left. Deflection will be left. So means polarity gets reversed. So this is explained on the basis of Faraday's law. Faraday then immediately given a law known as Faraday's law of electromagnetic induction. Now we are talking about Faraday's law of electromagnetic induction. Should I rub it or you just take the, yeah. So after this observation, talking about Faraday's law of electromagnetic induction, Write down the heading, Faraday's law. Faraday's law of electromagnetic induction. EMI. Okay, easy to remember, EMI, electromagnetic induction. So in Faraday's laws of electromagnetic induction, actually the law is only one, but we can divide it into subparts. The first part is whenever there is a relative motion, or whenever there is a change in separation between the magnet and coil occurs. So you may write whenever, and actually what is happening, if you bring the magnet towards the coil, the field of the magnet keeps on increasing at the center of the coil, because when the magnet is away from the coil, its field is low, and when it is bringing, if you bring the magnet towards the coil, then magnetic field of this magnet is going to be increased. So B is changing. B is changing. So remember the flux phi, which is B into A into cos theta. Now think in how many ways you can change flux. Flux can be changed by changing B. So in that scenario, if you bring the north pole or south pole of the magnet, or the magnet is towards the coil, the field of the magnet is going to be increased here at the position of the coil. And so if there is a change in B, phi will change. The another way to change phi is to change A, area of the coil. If you have a coil whose area keep on changing, like you can increase or decrease the area, in that case also change in area will bring a change in phi. And if you rotate the coil in magnetic field, then theta will change. If you are rotating the coil in magnetic field, then angle, what is theta? Theta is the angle between magnetic field and area vector. And if the angle between magnetic field and area vector keeps on changing, then also that phi will be changing. And change in phi, whenever there is a change in magnetic flux, an induced EMF is produced. This is the basic theory. So change in flux is involved, magnetic flux. We are talking about the magnetic flux. So whenever there is a change in magnetic flux linked with the coil, occurs, an induced EMF or an EMF is always induced. An EMF is always induced in it. Now, induced EMF is inducing. Why inducing? Because you are not bringing in touch with the coil. The magnet is somehow some distance, lying at some distance, and separation, only the separation between the coil and magnet is changing. And so this EMF is induced in the coil. So an EMF is always induced in it. And the second scenario is, this is first part, the second part is the magnitude of induced EMF, depends on the rate of change of flux, change of magnetic flux. What I am telling you, if you have a coil and here is a magnet, if you bring it slowly, no doubt magnetic field linked with the magnetic flux linked with the coil is changing, but the rate is very small, d phi by dt. If the rate is slow, then induced EMF will be very, very low. But you can bring the magnet fastly. See, if you bring the magnet quickly, then the rate of change of flux will be large. And if the rate is large, then induced EMF will be also large. So that is the second point. The magnitude of induced EMF depends on the rate of change of magnetic flux. Actually, in generator, you might have seen RPM, round per minute. The more is the RPM, the more will be the induced EMF. And inside a generator, nothing happens. Two magnetic pole pieces magnet are placed, and the coil is rotating in the magnetic field. So the rotation of coil changes theta, orientation, that is angle between B and A, area vector. And because of that, phi changes. And if the RPM of the coil is very high, then induced EMF, a voltage generated, will also be very high. So the magnitude of induced EMF depends on the rate of change of magnetic flux linked with the coil. With the coil or circuit, whatever. And the third part is, third part. This induced EMF lasts in the circuit so long as the change in flux continues. What I want to say, if you have this coil and this is a magnet, now as soon as you start bringing this magnet towards the coil, now galvanometer is showing deflection. But the moment you stop the magnet, induced EMF will disappear. Means the pointer of the galvanometer, now it goes to zero position. That is, induced EMF will disappear. So the moment relative motion between the coil and magnet stops, then there will be no induced EMF. So this is the third point. So this induced EMF will last in the coil or circuit so long as the change in flux is involved. Change in flux is involved. Now, if you bring the magnet, suppose you have a magnet, this is a coil, it has some magnetic field here, area is also there. So B into A, flux is linked with the coil. But if the magnet is not moving towards or away, then flux linked with the coil remains constant. And if the flux remains constant, then there is no question of induced EMF. There is no question of induced EMF. So this induced EMF will persist, lasts in the circuit so long as the change in flux continues, so long as the change in magnetic flux continues. The moment magnetic flux becomes constant, now that induced EMF will disappear. The induced EMF will disappear. Yeah, got it? Clear? Do you have any problem? So this is, yeah. So whenever there is a change in magnetic flux linked with a coil occurs. So what does it mean? When you bring a magnet towards the coil, the magnetic field of this bar magnet keeps on increasing here because the distance of pole with the center is decreasing. So magnetic field is inversely proportional to 1 by r square something. So it obeys the inverse square law or something like a magnetic field due to a magnet. So it is something 1 by 4 pi epsilon naught m by r cube. So if you decrease distance of magnet from this position, I mean center of the coil, then the magnetic field of the magnet will keep on increasing here. So increase in magnetic field will increase phi, flux. And whenever magnetic flux linked with the coil changes. So how can you change the magnetic flux? There are three different ways. By changing magnetic field, by changing area of the coil, by changing theta, the angle between magnetic field vector and area vector. Okay. So the first part is whenever there is a change in magnetic flux or whenever magnetic flux linked with the coil changes. Now some induced EMF is produced in the circuit, always produced. This was the first part. Now second part is the magnitude of induced EMF depends on the rate of change of magnetic flux linked with the coil. How fastly you are changing the magnetic field. I mean how fastly you are changing the magnetic flux. So suppose the magnet is lying here and coil is at this position, then the flux is suppose 2 Tesla meter square. And when you bring the magnet here, then the flux becomes 10 Tesla meter square. So what is the change? 10 minus 2, that is 8 Tesla meter square. And if this change, if you are bringing the magnet slowly towards the coil, slowly. So you suppose you have given 10-20 seconds, and the same magnet can be brought quickly. So in how many seconds you have changed the same? The flux is changed by the same amount, say within 1 second, within 2 seconds. Earlier it was changed in 20 seconds. So in which case the rate will be, the rate means d phi by dt. If dt is small, then d phi by dt will be large. So more is the rate, more will be the induced EMF. You got my point? More is the rate, more will be the induced EMF. So mathematically, you can write it. Mathematically, this can be written as flux phi, induced EMF denoted by a symbol E, something like this. E is equal to phi 2 final flux minus initial flux with a negative sign divided by T2 minus T1. And if phi 2 minus phi 1 is represented by d phi, small change in flux taking place in a small time interval dt, so then it is minus d phi by dt. Remember, this phi is phi b, magnetic flux. It is not the electric flux. So changing magnetic flux will generate an induced EMF, electric field, something like this. So minus d phi b by dt gives you induced EMF. Now this negative sign is due to the fact, negative sign indicates that induced EMF has always opposing nature, always opposing nature. And it was later on explained by Lenz. So it is explained by Lenz rule. Lenz, another scientist. Lenz's law, Lenz's rule. So what is Lenz law? What is Lenz rule? Just I will give you the concept. Now take the snapshot. I will change it. E is equal to minus d phi by dt is nothing but Faraday flux rule. Faraday flux rule. Now we are changing. Now we are moving towards Lenz rule. Lenz rule. Rule or law, whatever. Lenz rule. It states that the induced current, if the circuit coil is closed means if you connect it, its two terminal across the ends of a galvanometer, then it is a closed circuit. So if the coil is closed and a magnet is brought near the coil or taken away from the coil, in both the case induced current is there. But direction of induced current, in which direction it will flow in the coil, so that depends upon, actually it flows in such a way that it will oppose the very reason, the very cause which produces it. So what is the reason that will oppose? Just I am showing first the example and then I will lastly state the what is rule. Now if you have a coil, okay, you can close it or you can consider this hole connected. This is a coil. and this is a closed, the whole closed loop. Okay, then a magnet is lying here, north, south. You are bringing north pole toward this side. Then the reason is, since north pole is coming towards the coil, so this in this coil there is an induced current. Since it is a closed circuit, so then the current will flow. And if it is an open circuit, then induced EMF is there. EMF is there. But the moment it is closed, these two ends are closed, then induced current will flow. And the direction of flow of induced current will such that it will oppose the very reason, the very cause which produces it. So reason is, since north pole is coming towards this one, so this face of the coil should develop north polarity. So if this pole, this face is developing north polarity, the north will repel the north. So this way it can oppose the reason. This way it can oppose the cause, which is producing the current. So the current flowing through this coil will be automatically in anti-clockwise direction if you are looking from this side. Okay? So it is in anti-clockwise. So if it is in anti-clockwise, for me, if the current is anti-clockwise and we are towards the side of magnet, then this will be behaving as north pole. Okay? So current carrying loop behaves as a short dipole, whose one face is north, other face is south. So this face will then behave as north because north pole is coming. So then north will repel this north. Okay? On the other hand, if north pole is brought away from the coil, then the current flowing through the loop will be such that it will oppose the reason. Since south pole is going away, so north pole is going away, so south pole will be developed here. Because south pole will attract the north pole. So this way it can oppose the reason. So in other figure, if you, okay, now closing it. Now we are bringing north pole, south pole. Now magnet is brought away. So since north pole is going away from the loop, so the induced current in the coil will be in clockwise direction. Why? If it is clockwise, then this face, observing from the side of magnet, so this face should behave as a south pole. Then only south will attract north. So this way it is opposing the reason. The reason is, since you are bringing the magnet away from the coil, so this coil, the flow of current will be such that it will oppose that reason, that very reason which produces it. So why the induced EMF is produced in the coil? Because magnetic flux linked with the coil is going to be decreased. And when you bring the magnet towards the coil, then magnetic flux linked with the coil is going to be increased. So in first case it is increasing, in second case magnetic flux linked with the coil is decreasing. So accordingly, this face will behave as south, this face will behave as north. Accordingly, the direction of current will be clockwise, anti-clockwise, as seen from the side of the magnet. But the person whosoever is standing this side, increasing, if you bring the magnet towards the coil, the field of the magnet at the center of the coil keeps on increasing. Because the smaller the distance, more will be the field. If you are closer to the magnet, the field of the magnet will be more. And if you are going away from the magnet, the field will be less. Is there any doubt? Yeah, am I clear to you? No, this north pole is developed because you are bringing the north pole towards the coil. So this phase should develop such a polarity so that it can oppose the reason. Reason is north pole is coming towards the coil. So how can this coil oppose this reason? By developing north here. And you know, similar pole repel each other. But think about this scenario. When you bring the magnet, say north pole, away from the coil, then north, so this pole will be such that it should oppose the reason. So reason is north pole is going away, so how can you stop? How can you oppose it? So by developing South pole. South will attract the north. So this way the reason is going to be opposed. Am I clear to you? So why the negative sign was given in Faraday laws? You try to understand this fact. That negative sign is because of the fact that the induced current in the coil will flow in such a way that it will always oppose the reason, the very cause which opposes it. Now ready to write the Lenz rule. So statement of Lenz rule, it states that the induced current so produced in a coil due to change in flux, change in magnetic flux, will flow in the coil in such a way that it opposes the reason oblique cause which produces it. So this is very simple. So whatever is the reason, the induced current will flow in such a way, in such a direction that it should oppose the reason. Whatever is the reason. If the north pole is coming towards the coil, then this polarity will be developed in such a way that it will oppose. If north pole is going away, then this polarity will be such that it will oppose the reason. So then it will be south. Accordingly, the deflection in the galvanometer is opposite. Suppose here it is right side, then here it is left side. This is what the Lenz rule is telling. Now, to have a clear concept of Lenz rule, I am starting some more example, then it will become more clear. You just check the snapshot and I will move further. Okay. Done. So, by citing some more example, it will be more clear. Now, I am not rubbing the law. Law is remaining there. Suppose you have a current carrying wire through which a current I is flowing. And remember, this current I is a constant current. Say steady DC. A steady DC. DC can increase or decrease, but DC cannot change its direction. So if you have a steady DC, that is a constant DC, and if you have a loop, suppose here is a loop, and you place the loop above this wire, say in this position. Or if this is the wire, then you place the loop like this. You place the loop just below the wire, above the wire. And then I is constant. Now if you place the loop here, then what should be the direction of induced current? What should be the direction of induced current? Remember that this current carrying wire has some magnetic field. That is mu naught by 4 pi 2I by R, if this distance is R. So this wire has some magnetic field. So magnetic field is there, so flux linked with the coil is also there. Now think about the direction of induced current. In which direction the induced current will be generated in the coil? Find the direction of induced current. Find the direction of induced current. Your answer should be in clockwise or anti-clockwise direction. Find the direction of induced current. Induced current in the coil. In the coil. Is there anybody who can answer it? Yeah? Who can answer it? Clockwise. Anybody else? Anybody else? Yeah? Okay, someone is telling clockwise, someone is telling anti-clockwise. Now think, there is a magnetic field. Magnetic field of this current carrying wire at the center of this coil. So then flux phi is equal to B into A. Now think, this B is not varying because current I flowing through the straight wire is constant. It is a steady current, a steady DC. So if current is not changing, then why the magnetic field of the wire will change? You know, magnetic field of infinitely long wire is mu naught by 4 pi 2I by something. This distance is R, then R. If R remains constant, is there any question for change in B? No, B is not changing. Area of the loop is also not changing unless and until you change it. This is also constant. So magnetic field is there, but area is also fixed, constant. So what about flux? Flux will remain constant. And if the flux remains constant, then why do you think about the direction of induced current? This induced current or EMF persists in the circuit so long as the change in flux continues. The moment the change in flux stops, now there is no question of change in, that is induced current, induced EMF. So no induced EMF. Here, no induced EMF. No induced EMF. So your answer, clockwise, anti-clockwise, both the answers are wrong. Because flux phi here is constant. And if B and A, both the quantities are constant, then induced EMF, which is minus d phi by dt, you just tell me, if phi is constant, then d by dt of phi is what? 0. And if induced EMF is 0, no question of induced current. Induced current I, which is E by R is the resistance of the coil, so then it will be also 0. Yeah? The second question, you have a coil, see, and you have a magnet also. Now, when magnet is falling, suppose this is North Pole. Better to draw the diagram like this. So here is your coil and magnet is falling like this, okay? Then the question is, what is the direction of induced current in the coil? What is the direction of induced current in the coil? Yeah. Yeah. What will be your answer? Anti-clockwise. Very good. So again you are wrong in answer because the coil is not closed. See, magnetly, the coil is not closed. Yeah. That's why special. Since you are studying physics, you will be a doctor, future doctor, engineer. So you must notice these types of things, minute things, eagle's eye. Okay. So since it is not a complete loop, it's an open loop. So if it is an open loop, there is no question of induced current. Current will flow only when the circuit is closed, loop is closed. But induced EMF will be there. Induced EMF will be there. And you can't say the induced EMF has direction clockwise or anti-clockwise. The induced EMF direction means plus minus. Terminal will be plus and minus, as if it is a battery source. But unless and until you connect with a closed circuit, no current will flow. So no induced current. So whether the magnet North Pole is falling towards or away or South Pole is falling towards or away, in any case, unless and until it is a closed loop, no question of induced current. No induced current. Induced current. Why? Because the circuit is, coil is open. Because the coil is open, not closed. You are the future scientist. You are the future doctor. You are a future engineer. So if you don't notice all these sophisticated things, how will you be a great doctor or a great engineer? Okay, so now the third concept I am giving you. We have some 5-7 minutes time. Okay, take the snapshot. I will rub the board. Yeah, yeah. Okay. Now, now I can rub this part. Now the question is, third question is, you have a straight wire and the current I is not constant. Now it is increasing. An increasing current is flowing through this infinitely long straight wire. And a loop is there, lying above the wire. Lying above the wire. Here is the scenario. If it is a current carrying wire, the loop is lying this way. Now, through this wire, increasing current is flowing. Now you have to find the direction of induced current in this closed loop. Though it looks open, but remember this is a closed loop. Assume it as a closed loop, and it is pressed like this. And then afterwards, I will put it below the wire. Then I will ask what is the direction of induced current in the coil or the loop. Who will answer? Is there anyone? Direction of induced current. Yeah? Okay. I should answer it. The current I is increasing. Now, anti-clockwise? Okay. So, is there any logic behind it or you are just guessing? Is there any logic? No, I don't have so much time for waiting for your answer. Okay. Now think about the magnetic field of this infinitely long straight wire. We have already written it as mu naught by 4 pi 2I by, if the distances are, by r. Okay. Now current is increasing. Obviously B will also keep on increasing. B is increasing. Now can anyone tell me what is the direction of magnetic field of this straight wire at this point? Yeah? It's a current carrying wire. Now into, how you are telling it's into current? So we are here. I can show you. So your finger, okay, this is wire. So when it comes to this position, then it is towards the observer, up the plane, okay. So this is the magnetic field of this straight current carrying wire, and this magnetic field is increasing because current through the wire is increasing. A straight wire, the current is increasing. So flux phi, which is BA cos theta, here BA, direction of B and direction of A is along the same direction, so it is BA only. Okay, so if B keeps on increasing, flux also keeps on increasing. Now this coil or the loop has tendency to oppose this increase in flux. So how will you oppose this? By decreasing B. Now how can you decrease B? You know B is a vector quantity. Magnetic field is a vector quantity. So if, because of the Lenz rule, negative sign, that states. So induced, if there is an induced current, then induced current will flow in such a way, in such a direction, that it has a tendency to always oppose the reason, the cause, very cause which produces it. So from Lenz rule, it is well known to you. Now think about the direction of current, the direction of magnetic field at the center of the loop. It is towards the observer, up. So this magnetic field is upward or towards the observer. So the loop will set its own magnetic field opposite to the direction of this field. Why? Because magnetic field is a vector quantity. So if two vectors, the moment they become opposite to each other, the net magnetic field will reduce. So if the net magnetic field gets reduced, the flux opposition, that is, earlier it was increasing, now it is opposed because B is decreased. Yeah. So B, yeah, this is the magnetic field of this straight wire. Now the magnetic field of the current, this loop, will be opposite to this. Then only the net magnetic field will reduce. Since I is increasing, so magnetic field is increasing. You have to stop this increase. How will you stop it? By applying a field opposite to this field, I mean along this direction. So if the magnetic field of the loop is along this direction, think about the direction of current. It should be clockwise. So it should be clockwise. Then magnetic field of the current carrying loop will be cross. So upward, downward. The two fields opposite to each other, therefore net field will get reduced. And if the net field get reduced, then flux, instead of increasing, now its opposite will be there. So increasing is somehow retarded. That's why the direction of induced current will be along clockwise direction. Now if you place the same loop below this wire, or you have another loop and is placed below the wire. Below means, here is the scenario. Earlier it was like this, now it is like this. So in this scenario, think magnetic field of this straight wire is into. Now at the center of the loop it is along this direction. I mean perpendicular to the whiteboard, pointing inwards. Now I is increasing, so this magnetic field is increasing. Now the loop will set the current in such a way that it will oppose this region. So oppose this magnetic field. So magnetic field is inward, so the loop will set the magnetic field in the upward direction. Upward, this side. So it should be anti-clockwise. It should be anti-clockwise. Yeah? Anti-clockwise. Remember, if you have this I decreasing and the same scenario, two loops placed, one above the wire, other below it. Now in this scenario, guess the direction of current, induced current in the two loops. Yeah? Anti-clockwise. Opposite of this, it should be clockwise. So how will you remember these things? The fact is, if current is increasing, then actually it is not happening, but it is easy for you to keep in mind. See, if it is I is increasing, then current here will be such that it will oppose the region. So current is along this direction and I is increasing, so current is opposite to this current. And if the current is decreasing, then current here in the loop is along the direction of current in the wire. So two currents in same direction means they will help to decrease the magnetic field. And that's why it is easy to remember, if I is decreasing, then along the direction of the current of the wire, see, along the direction of current of the wire, if I is increasing, then scenario gets reversed. Then it will oppose. Am I clear to you? But this is not the reason. This is not the factual information. Fact is, it has somehow opposed the reason. I increasing, magnetic field increasing. So the loop will develop magnetic field in such a way that it will oppose the increasing magnetic field here. And that's why loop is applying field into. So one upward, the other is downward, so the net field gets reduced. Here I is decreasing, so magnetic field here is decreasing. Now the loop will have magnetic field in such a way that it will support the magnetic field. So magnetic field is upward. Now if the current is anticlockwise, then this is also magnetic field of the loop is also in the upward direction. Magnetic field being vector quantity, if they are in same direction, gets added. So this way it can oppose the reason of decreasing of the current magnetic field. So if the loop is also applying magnetic field in the same direction, so the moment two vectors are in the same direction, the resultant will be plus. Same thing happens here. See, magnetic field of this wire is into. Now I is decreasing, so magnetic field here is decreasing. So the loop will develop magnetic field along the same direction to oppose the decrease. So magnetic field in the loop, so current should be clockwise direction, then only the magnetic field is along this direction. And if the magnetic field is along this direction of the loop, then magnetic field of the straight wire is also cross. So two cross, so magnetic field gets added. So decrease in this magnetic field because of the decrease in current is somehow opposed. This is what the Lenz said. Yeah, understand?